Welcome to Math 31. We are looking at lesson 1.2 where we look at the limit of a function. Now, just before we start into this lesson, let's have a quick look back at what we did in our previous lesson where we were looking at this tangent problem. And with the tangent, we were finding a way to figure out what is the slope of this tangent line, and then we also figured out the equation of the line. So what we said we would do is we would take this point Q and we would move it closer and closer to the point P. And as Q got closer and closer to the point P, this secant line that was connecting P and Q, that line would be approaching this tangent line. Let's take a minute to look again at the Desmos illustration of this. So here we see the point P, which is a fixed point, and the point Q, which is a variable point, and we're going to move this point Q along our curve and say, well, for this x coordinate, so if x was 1, I would get this as my slope for the secant line. If x was 2, that would be my slope, but the closer this x value gets to this -3, which is the x coordinate for P, then the closer my secant line comes to being exactly the tangent line. And we discovered that if we actually reach that point, our line gets undefined because the change in y is 0, the change in x is 0, our slope equation goes to 0 over 0. So we could only look at a limiting value as q got closer and closer to p, either from the right side here, and we could also do it from the left side here as we get closer and closer. From both sides, the slope is approaching the slope of that tangent line. So we said to find the slope at P, we needed to find the limiting value of the slope of the secant line, MPQ, as Q approached P. And the notation we used was we said MP would be the slope of this tangent line, so the slope at P. And so we'd say the limiting value of our slope as Q approached P. Another notation we looked at was when I did this y2 minus y1 over x2 minus x1, as x2 approaches x1, what is the limiting value of this slope equation? Or we could look at it in this form, where we had the change in y over change in x representing our slope, and as this change in x approached 0, then this limiting value would give us the slope of our tangent line. Well, then we did this example. And so here it was fairly rough working through, but here as I look at my x values, I have x that's 4, and I was interested in finding the slope at the point P, so the slope of the tangent line there. So I had 4 approaching 3, and then here I had 2.1 and was approaching 3 again, and I looked at my slope value. So again, this side of the table are slope values, not y values, and here my slope value looked like it's approaching 6, from 4 as I approach 3, and from 2 as I approach 3, it looks like my slope approached 6, and so we said the slope of the tangent line was equal to 6. Now, many of you recognize that we could have done this in a different way algebraically. As we looked at this slope equation here, you saw that, oh, there's a common factor that we could find and cancel out. That's the direction we're going today. So today what we're doing is we're taking a bit of a sidestep, and we're going to look at the limit of any function. So we're not specifically looking at slopes of tangent lines, we're just looking at how do we find limits of functions. So let's start by looking at the notation that we use. So here we can see the notation. So we have this LIM, which means we're looking for the limit of this function f of x. And we want to know, what does this function approach? In other words, what does the y value approach as my x value approaches a? And we'd say the limit of this function as x approaches a is equal to L. Now, notice here that we do use an arrow here as we're saying x is approaching a, but here we're saying, well, x, I should say f of x, the function, is approaching L, but we don't use an arrow here. We just say that the limit is this value L. So then, as we look at the words on the right, the limit of the function f of x as x approaches a is equal to L. Now, sometimes we switch it up a little bit and we'll say the limit as x approaches a of the function is equal to L. So we use all of those phrases, just not necessarily in this order. So again, this is saying as our x value is approaching the value a, this function is approaching the value L. Our next definition here is looking at what's called continuity. So we say that a function is continuous at the point where x is equal to a if and only if the limit of the function as x approaches a is equal to f of a, so it's equal to the value of the function at a. So let me say that once more. If the value of the limit, in other words, as x approaches a, if the function value is approaching f of a, then we say our function is continuous. Well, let's look at that as we look at these examples here. These examples aren't asking about continuity, they're just asking about limits, but we'll talk about continuity as we do these as well. So here for question number 1, we want to know the limit of the function as x is approaching 1. So I look at an x value of 1, which is right here, and I'm going to say, well, as I approach an x value of 1 from the left side, what happens to my y value? Well, it goes up a little bit and then comes down, and it looks like it's approaching here a y value of 4. And then as I approach from the right side, what's happening? Well, my function comes up here, and again, it looks like it's approaching that same value of 4. And since it's approaching the same value from both sides, we would say the limit of this function as x approaches 1 is equal to 4. Now notice also at this point, this is the value of the function as well. So we'd say this is equal to f of 1. So that's the value of the function. So we'd say that this function is continuous at x equals 1. Again, that's not what this question was asking. This question was just asking what's the value of the limit, and we'd say the value of the limit is 4. But to help us understand continuity, I thought we'd just talk about continuity related to this example. Well, let's go back up here. We'll finish off with these bullets, and then we'll come back to that example. Any polynomial function is continuous everywhere, which means that the value of the limit is equal to the value of the function at any point on that function, or so any of the x value. So that's partly because our polynomial has a domain of all real numbers, but that's not the only condition that we have. Next, a rational function, which would look like a polynomial p of x divided by a polynomial q of x. It's continuous everywhere for every value of a, except those values of a that make the denominator equal to 0. So that means the limit as x approaches a of p of x over q of x is equal to p of a over q of a. Now let's come back to our example where really we just want to find the limit. We'll look at continuity again more in another lesson. But that was just a starter glimpse at continuity. Question number 2. We want to know the limit of our function f of x as my x value approaches 3. Well, now as I approach 3 from the left-hand side, my curve comes down here and it looks like it's approaching a y value of 1. And as I approach 3 from the right-hand side, my curve comes up like this and it looks like my y value is approaching 1. Now the function isn't defined there, but when we're looking for limit, we don't care what the function is defined as. For continuity we care, but for finding the limit we don't care. We just want to know from the left side and from the right side, is our function approaching the same value? And it is. So we would say the limit of the function f of x as x approaches 3 is equal to 1. Now if we looked at here where x is approaching negative 3, we get a different situation Because as I look at my left side, so I'm approaching 3 from the left here, my y value is going up and it's approaching positive infinity. As I look at coming from the right-hand side, as my x value comes this way, my y values go down here and they're approaching negative infinity. Well, they're not approaching a finite value and they're approaching different infinities. So we would say that this limit does not exist. And often I'll abbreviate that just with a DNE to represent does not exist. Well, let's look at some properties of limits. We may not go through all of these in detail, but you should study these and be familiar with them so that you're able to use them. So this is on page 13 in your textbook. So here this is saying that the limit of the sum of two functions is the sum of the limits of the two functions. Now you might look at this and say, well, yeah, that makes perfect sense. It looks like we're just distributing this limit in. No, we are not distributing. The distributive property says that if I have a times b plus c, I can multiply this a, so the a is being multiplied to the product, I can distribute it in to say this is ab plus ac. Now this is true, but what's happening here? Is this limit being multiplied to this sum? No, this limit is an operation, and this operation is being applied to this sum. So what this property says is if I have the limit of a sum, I can find the limit of each function separately, and that will give me the same value as if I added the functions together first. Okay, so don't think distributive property because that's not what's going on with this situation. Number two, similar idea if we're subtracting two functions. Here, if I have the limit of some constant c, so here we're assuming that c is just some number times the function. This I can actually pull out in front because it's not going to affect the value of the limit if I multiply to the function first, or if I multiply to the function after I find the limit. So I could find the limit first, then multiply it to c. We find that simplifies some questions, and it'll make more sense as we work through examples. Here's another situation where we can see that this is definitely not the distributive property because distribution works when we have a sum or a difference, as in 1 or 2. But in this case, it's just saying if I have the product of two functions and I take the limit of the product, the result will be exactly the same as if I found the limit of the first function as x approached a, and then just multiplied that to the limit of the second function as x approached a. Same thing for division. And then here, this one. If I did the limit of a power where the base is some function, what I can do is I can find the limit of the function as x approaches a, and after I find that limit, then I can raise it to the exponent as long as n is a positive integer. Again, all of these will become more familiar as we use them in examples. Similar idea with number 7. We could just write this with an exponent of 1 over n, which would make it just like the property in number 6. All right, so now let's look at some examples. How do we find the limits of functions? Well, the first thing that we will do is we will always begin by saying, well, can I just plug this number in? So kind of like over here where we looked at this first example, to find the limit of this function, it turned out to be just the value of the function. So here I could just plug in the number 1. If I had an equation for the function, it would give me a 4. That would be the value of the limit. That wouldn't work for number 2 because the value of the function is not equal to the value of the limit. So sometimes we can just plug in a number, sometimes we cannot. For question number 4, we can just plug in the number. If I substitute 2 in place of my x, I get 2 cubed, and then here I have a 2 squared. There's no reason for me not to plug those numbers in. It doesn't give me an undefined function, so I can just evaluate, and I'll get the answer that the limit of my function, x cubed minus 3x squared, as x approaches 2, is equal to negative 4. Number 5, similar idea. Now, here I have a rational expression. It's not defined when x is 3, but if x is approaching 2, there's no problem. I can just plug in the value for x and then evaluate. So I replace all the x's with 2, evaluate, and I find out the limit of this function as x approaches 2 is equal to 4. Number 6. Now this function is undefined at some points, but when x is equal to 2, what happens? Well, let's try just substituting in. 2 squared is 4 times 3 will be 12 minus 8. Oh, the function is defined there, so I get 12 minus 8 as my radicand. Square root of 4 gives me 2. Question number 7. Well, here it's the same as what I had in number 5, except now my x value is approaching 3. If x is approaching 3, my denominator is going to go to 0. So if I were to try plugging in those values, plug in the 3 in place of all the x's, what I get is 0 over 0, which is undefined. But as all of you expert Math 30-1 students recall, if we had a situation like this where it looked like numerator and denominator were both going to 0, it meant we had a common factor. So we will factor out the x squared in the numerator, and then we can see that we have this x minus 3 and that x minus 3, and they can cancel each other out. When they do, I'm left just with this x squared. Then I can plug in the 3, so I have a 3x squared, which evaluates to give me a 9. Now at this point, I would like you to notice the limit notation, where we kept it, and where we got rid of it. So here at this point, I'm saying x is approaching negative 3. Here I still have my variable x. I'm not replacing x's with 3's yet, so I have to make sure I keep this limit notation. In my next line, I replace the x with a 3. Once I replace the x with what it's approaching, I don't want to write the limit notation anymore. So make sure you take note of that as we look at the next few questions. But first, here's the tip. If I have a rational equation and I get something like P of A over Q of A looks like 0 over 0, we want to look for a common factor of x minus A. So again, this kind of goes back to the factor theorem, where if P of A is equal to 0, that tells me that x minus A is a factor of P of x. Similarly, if Q of A is equal to 0, that tells me x minus A is a factor of Q of x. Question number 8. Here I have a limit of this function as x approaches negative 4. Well, my denominator goes to 0. What happens to my numerator? Well, 4 squared is 16. Oh, and negative 4. So negative 4 squared is still a positive 16. Negative 4 times negative 2 is positive 8. 16 plus 8, 24. Minus 24, 0. This looks like 0 over 0, so we want to factor in order to find a common factor. And since x is approaching negative 4, we're expecting this x plus 4 to be the common factor, and we can see it here. So at this point, we can see that this x minus 4, that x, I should say the x plus 4s, both cancel out, which gives me the limit as x approaches negative 4 of x minus 6. Now another notation here, take note that I'm keeping brackets here. If I didn't have brackets, it just looks like the limit as x approaches negative 4 of x, and then that whole limit has a 6 subtracted from it. That's not the case, so we do want to make sure that we keep the brackets here. And as I mentioned on the previous page, here once I do the substitution, so as soon as I replace this x with the -4, I don't have the limit notation anymore. I have to keep that limit notation until I do the substitution. Now that can be a frustration for students because some questions get really long, and writing this limit as x approaches -4, like 5 or 6 or 7 times down the page, gets kind of tedious. But on an assignment or a test, marks will be deducted if you don't show that you know when to keep the limit notation and when to get rid of the limit notation. Let's go on to question number 9. Again, I'm going to do a test. Can I just plug in the -3? Well, if I was to plug in a -3, I would get 9 minus 9 in the numerator, 0. 27 plus 18. Actually, this would have been a -27 because it's a -3 cubed, plus an 18 minus 5 times -3 will be plus 15 minus the 6. And what do we get? We get 0. So again, we're getting 0 over 0. We want to find a common factor. You look at this denominator and you say, oh dear, it's a cubic. We need to figure out how we're going to factor this. But we already know that when we have an x value of -3, this polynomial equals 0. So we've already done the first step. We've used the factor theorem, and we know that when we come to doing synthetic division, we can do it with a -3 as our x value. So that helps us because we've already figured that out. So again, synthetic division, there I've set it up. Once I go through the steps, bring down the 1, remember, and then -3 times 1 gives me -3, and then add. Multiply the -3 times -1, I get +3, and I add. And again, I'm ending up over here with this value being 0, which is perfect. That's the remainder of 0 that I was hoping to find. So I know that I can rewrite my denominator as x plus 3 times x squared minus x minus 2. Can I factor this quadratic further? Well, maybe, but I don't care, because what I've found here is the common factor that I need to cancel out. So I can cancel out this common factor, and I'm left with the limit as x approaches -3 of x minus 3 all over x squared minus x minus 2. Now, just notice here I didn't put brackets around this. Why? Because this line separating numerator from denominator is a grouping symbol. It groups all of this stuff in the bottom and all that stuff in the top, so the limit is the entire rational expression. And once we have this, now we should be able to plug in the -3. -3 minus 3 is not 0. So if we plug in the value, and notice we've gotten rid of the limit notation as soon as we plug in that -3, evaluate, simplify, and we have the limit for this function as x approaches -3 is equal to -3/5. So back in Math 30-1, the strategy that we use to find the y-coordinate for a point of discontinuity, that's essentially what we're doing here, but now we're using proper mathematical notation to say that we are finding the limit of the function as x approaches this number. But this would be the y-coordinate for the point of discontinuity when x is equal to -3. On to question number 10. And as you look at question number 10, I can hear the cheers in the background where we have this binomial to the exponent 5, because I expect you're all really excited to expand this. It's a binomial to the exponent 5. Hopefully you thought binomial theorem and maybe even Pascal's triangle. So again, if I have an exponent of 5 here, then when I think of binomial expansions, here this is like my binomial to the exponent 0 would equal 1. This would be my binomial to the exponent 1, to the exponent 2, 3, 4, 5. This is the line I'm looking for, and that gives me my coefficients for the expansion. So that binomial theorem that we learned in Math 30-1 is useful to save us a ton of time in figuring out this expansion. Now, what didn't I do? I didn't plug in 0 for h, but let's do it. 0 for h, denominator 0. 0 for h here, 2 to the 5th is 32 minus 32, 0. So yeah, I do need to expand it and look to see if I can find a common factor of h. So here's what I get from the this expansion here for Pascal's triangle. So here are my coefficients, the 1, 5, 10, 10, 5, 1. So that red stuff corresponding to this line from Pascal's triangle. I still have the minus 32 up there, so I have minus 32 all over the h, and I'm looking for the limit as h approaches 0. Then you'll remember from the binomial theorem that I look at the first term in the binomial, which is a 2, and that will be multiplied to each of these terms, starting with the 2 to the 5th, 2 to the 4th, and so on. So I get these values. There we go. 2 to the 5th, 2 to the 4th, 2 cubed, 2 squared, 2 to the exponent 1, 2 to the 0. I just didn't bother writing it in to save some space. That second term starts with an exponent of 0 and then increases the exponent each time. So h to the 0, h to the 1, h squared, h cubed, h to the 4th, h to the 5th. There we have the binomial expansion of 2 plus h to the exponent 5. If you need to, pause the video, but I'm going to continue on here. When I evaluate to expand that, here's what I get. Wait, that's not quite what I get. I've skipped a step. Well, we'll keep this visible while I go back and talk about what's going to happen. So I already know, there we go, that at this point I have 2 to the 5th. 2 to the 5th is equal to 32. All these other terms have h's in them, and then I have this minus 32 at the end. So this positive 32 at the start and this subtract 32 at the end are going to cancel out. So that's why it's not showing up here in my next line. Here, if I do 2 to the 4th, 16 times 5, that's where this 80 comes from, times h, there's the h. 2 cubed is 8, times 10, 80 times h squared. 2 squared is 4, times 10, 40 h cubed, and so on. Well, now that this constant here and that constant there have canceled out, all of my terms have an h in them. And so I can factor out an h as a common factor. Once I've factored it out as a common factor, it can cancel with my denominator. That was my goal because as h approached 0, my numerator went to 0, my denominator went to 0. Here's that problem common factor. So here's what I get. Limit as h approaches 0 of this sum. And as h approaches 0, what's going to happen? Well, this h is going to become a 0. So that disappears. This h becomes a 0. That disappears. H cubed, 0. That disappeared. This 0 to the 4th, that term disappears. All we're left with is this 80, and that will be the value of the limit. Again, notice we kept the limit notation all the way until we substituted the 0 in, and then we could just write down our numerical answer once we substituted the 0 in place of all the h's. Well, we are not quite done. Let's look at another example. Once again, we have the limit as h approaches 0 of some function. If I plug 0 in, square root of 16 is 4. Minus 4, 0, over 0. Yep, there's a problem. Well, as we look at this, now we have a situation that we looked at in the review and preview where I could rationalize this numerator and get to a point where those h's will cancel out. So all that work we did with review and preview and conjugates now applies. Here's where we're using it. Again, the conjugate. Here I have a minus 4. So here I'm going to add 4, numerator and denominator. So I'm multiplying the whole thing by 0. What happens when we expand it? Again, notice I'm keeping the limit notation as h approaches 0. The 16 plus h under the square root times this 16 plus h under the square root cancels out. We get 16 plus h. Negative 4 times 4 minus 16. And we are getting this 16 canceling out with that 16. All we have left in the numerator is that h. And that h should cancel out. So here I rewrote it in the next line. If you don't rewrite this line, that's okay. But here we can see these h's canceling out. And once we've canceled them, then we are at a point where we could just substitute 0 in place of this h in order to evaluate. There we go. We get 1/8 as the value of the limit. Again, as you need to pause the video in order to get down the details of the question, but to keep the video from getting too long, I will continue down. Here's another challenging question. H is approaching 0, so I have a half minus a half, 0 over 0. What do I do? Well, I look to see, can I simplify this numerator? And I will by multiplying the numerator and denominator by the common denominator of 2 times 2 plus h. So again, as I look in the numerator, I want to get rid of the fraction over top of a denominator. So multiplying here, when I distribute that into the numerator, this is what I'll get. Remember that in my multiplication process, I'm thinking of all of this as being over 1. And so these denominators aren't changing. These values, the 2 times 2 plus h, are just multiplying to the 1s that are in the numerator, and that's what we get here. Then we can see, the 2 plus h here will cancel out, the 2 there will cancel out, and we've cleaned up our numerator so that we don't have a fraction in the numerator anymore. And we can see that I'm going to have a 2 minus a 2. So again, those constants are going to cancel out, and we'll just be left with a negative h. Now, if you'd like, you could take this negative and distribute it into the brackets here to get rid of the brackets. So that would make our numerator look like a 2 minus h. And then these 2's cancel out, and that's where we're getting this negative h from in our next line. Notice in the denominator, I didn't bother expanding. So again, it's that same strategy we've used since Math 30-1, where my goal is to change the numerator, so I'm not expanding the denominator, I'm keeping it in factored form. Factored form turns out to be useful because again, here, these common factors of h cancel out. That was the problem why we couldn't just plug in a 0 for h, but now we'll be able to substitute the 0 in. And I didn't write in the extra line, but this h here is approaching 0. These two h's canceled out, leaving us with a negative 1 in the numerator and the 2 times the 2, giving us the 4 in the denominator. Well, there are a lot of examples and getting fairly complex. So I think it's time for you to try some questions. So here, these final 2 pages of our notes are check your understanding questions. So I'd like you to work through all of these questions up to number 17. And once you've finished up to number 17, then you can restart the video and we'll have a look at question number 18 together. So pause the video at this point and then restart once you've finished a few or all of these, depending on how far you want to go before you get some input. Okay, pause video now. For question number 13, if we plugged in 0 for x, we get 1 minus 1 is 0 in the numerator, 0 in the denominator, so we make use of the conjugate in order to rationalize the numerator, getting to a point where we have this common factor of x that we can cancel out. Again, make sure you kept the limit notation until you replaced this x with a 0, and then you had the square root of 1 is 1 plus 1. 1 plus 1 gives us 2 in the denominator. For question number 14, if we plug a 2 in, we get 2 cubed is 8 minus 8, 0. Denominator, 4 minus 6 is negative 2 plus 2 is 0. Yup, 0 over 0. So we want to factor again. We can use that difference of cubes rule that we have on our formula sheet. We can see now that common factor of x minus 2. When we cancel out that common factor, then we're just left with the quadratic over the linear function. At this point, we can substitute the values in. So I didn't show the details, but that's what's happening. So if I was going to show another line, I would say that this is equal to 2 squared plus 2 times 2 plus 4 all over 2 minus 1. That gives me a 4 plus 4 plus 4 over 1. 12 is the value of the limit. Question number 15, again, as we plug in numbers, what do we see? Hey, we don't get 0 over 0 when we plug in numbers. So again, just a reminder, we always want to start by saying, can I substitute this 1 in place of the variables and evaluate it to get an answer? In this case, the value of our limit is the value of the function, which is equal to negative 1. Question number 16. This time when we plug in 0, 2 squared is 4 minus 4 is 0. Yep, we get 0 over 0. So we want to expand the numerator. And again, as we saw in previous questions, we get the constant as a positive, the constant as a negative. They cancel out, giving us terms with a common factor of h. Then we can pull out that common factor of h and then cancel it out. So these h's will cancel out. This h will go to 0, leaving me just with that 4 as being the value for my function, or the value for the limit, that I should say. Question number 17. Can I just plug in 3? 3 squared is 9 plus 3, 12. Why not? Again, we always want to see if we can just plug in the number in order to evaluate the limit. Let's go ahead here and look at this final example. Well, this final example is going to be similar to the first three in that looking at the graph is going to be the most helpful way to do this. We want to look as x approaches 0 from the left and from the right, what y value does our function approach? Does it approach the same y value? Well, hopefully your understanding of Math 30-1 lets you graph this without a calculator. Here's what it'll look like, and as I look at my limit as we approach from the left, we're going down towards negative infinity. From the right, we're going up towards positive infinity. So that shows that this limit does not exist. There we go. We've made it through this lesson. This video is only 40 minutes long. Whew, a long one. Really important to practice lots of questions in this section. So enjoy.